Cube map. So cube mapping is a very popular environment mapping technique. What is environment mapping? So environment mapping is somehow saving the light that is coming in from the environment. So if you have a fragment that we want to render, environment mapping can help us know what different light is coming in from the environment that contributes to the final illumination of that fragment. If we use an image to save those values, then this is also called image-based lighting. So we have an image and we sample the incoming light from that image. So this image can be drawn, so you can actually draw your own cube map, let's say in Affinity Photo, if you take layer, live projection and equirectangular projection. It can also be photographed, so let's say with a 360-degree camera that captures the entire 360-degree field of view. We could imagine it as like an entire sphere around the camera, so the different light coming in from all of those different angles. Or we could also render it. If we have our scene, we can put 6 90-degree cameras looking at each direction, and then we get 6 images, equirectangular images that represent the light coming in from all these 6 different directions. In Three.js there is a cube camera object that does exactly that, and in game engines sometimes you have things called reflection probes or reflection captures that also do that. They are called like this because the map we create is very useful specifically for reflections of the environment. So you can put those reflection probes in the scene, and when you have reflective surfaces, then the reflections for those surfaces can be sampled from the maps created by the probes. A cube map is one way to store that environment map. So the incoming light is stored in textures on the faces of a cube. There is one texture for the positive x, one texture for the negative x, one texture for the positive y, and so on. Overall, they make up the faces of a cube, which can be unwrapped like you see on the right here. When you render this with a cube camera, then all of those faces are the results of each of the cameras. Let's look at how we sample the cube map. So when we need to sample the light, we might have a situation like this, where the camera is over here, we're looking at this reflective object, it has a surface normal and a reflection vector. So we want to know what is the mapped reflection value at that direction. Over here we also have the incident vector. So to find the reflection vector, we just take the incident vector and we reflect it around the surface normal. This function in GLSL actually performs this mathematical calculation. It's incident minus 2 times the dot product between the normal and the incident vector times the normal. So how does this work? Because the surface normal is normalized, then what the dot product does is a scalar projection of the incident vector onto the surface normal. The incident vector is pointing towards our fragment. So to see the result that the scalar projection gives, we have to move it over here. So the scalar projection gives us this distance, the distance we need to travel to this point, but we also multiply it with the surface normal itself, so in the end we get a vector that is pointing over here. Next we take minus 2 times of that vector. This is shown over here. Next we add that to the incident vector, resulting in a vector like this. And this vector is actually the reflection vector. So this is how the reflect method works geometrically. Now when we sample a cube map, we actually make an assumption. We assume that the cube map is very far away from us. This will make sampling the cube map much easier, and usually these cube maps or environment maps represent some sort of a skybox or an environment that is far away, so far away that it can be represented with just an image. And besides just sampling it to get the reflections, you might actually put that image onto a big sphere or a cube that encapsulates your entire scene. So when the player is looking up at the sky, they will see the stars or clouds that you have in the environment map. This is often called a skybox. But still, when we're trying to render the reflections and we are sampling from that cube map, we make the same assumption that it's very far away, and our sampling point is actually the reflection vector taken from the middle of the cube map. So in the cube map space, the origin is in the center of the cube map, and we just sample from the direction of the reflection vector from that origin. We use that sampled value as the reflection value for the reflection vector down here. When the cube map is infinitely far away, then this offset here really doesn't matter. but you have to still keep it in mind, because if your cube map is not very far away, then the reflections will be a bit off. Now sampling the cube map works like this. First we find the major axis M. So we take the absolute values of the coordinates of the reflection vector. We find which of these is the maximum, and this determines the phase that we sample. So let's say that the y coordinate is the largest coordinate. This means that this vector from the origin is largely pointing at the, let's say, positive y direction, telling us that we need to sample from the positive y phase. The next step is to then divide the remaining horizontal and vertical coordinates by that maximum value. This will give us S and T, which will be in the -1 to 1 range, representing both the horizontal and vertical sampling coordinate. You can imagine it like this. If you have a reflection vector that is pointing at a diagonal, then its maximum coordinate, let's say the y coordinate, will be square root of 2, and the other coordinate, let's say the x coordinate, will also be the square root of 2. If we divide the x coordinate with the y coordinate, then we get 1, and well, this is pointing at this right corner of the positive y phase. Similarly, if we have minus square root of 2 and square root of 2, then we have a reflection vector pointing this way. If we divide it, we get -1 for this left corner. Of course, because of our phase is actually in the UV coordinates, we need to convert that -1 to 1 range into the 0 to 1 range, which is just done by adding 1 and dividing by 2. You might be still wondering, why does this division actually work? So we saw that the endpoints are correct, but what about the middle values? So let's look at this situation. We have a cube map face over here, and here we have the different reflection directions that are stored on the cube map face. For example, the direction over here, this orange color, this is stored at this location. So you see, we cannot just take, let's say, the x coordinate of this reflection vector and sample the texture from there, because that would be wrong. That would be somewhere over here, but the actual value is over here instead. So we need to find out what is the x-coordinate or the horizontal coordinate of this point. To do that, we use our old friend similar triangles again. So here we have the reflection vector. The length of this leg is the reflection vector's horizontal coordinate, because we are assuming that we are sampling from the cube map's center. And note that in the actual division, we are not just taking the length of this leg, but this is a signed value. So if our reflection vector would be on the negative horizontal axis over here, then this would have a negative sign, giving us values from 0 to -1 on the left. Next, this leg is the absolute value of the major axis coordinate, this cm that we calculated and that we're dividing with. And well, this big leg over here, this is just the length of r, because our triangle lies on this circle. Now we might not be sure of what length this actually is, so let's call this leg the scaled horizontal texture coordinate, S'. And of course, this entire length here is again the length of the reflection vector r. And now we can look at the similar triangle multiplications. So this RH divided by CM, RH is over here, CM, this equals the same value as this S' divided by the length of r. So those two ratios are the same. RH divided by CM is the same as S' divided by the length of r. But what is this S' divided by the length of r? Well, that is actually just the percentage along this face of the cube map. If the S' equals the length of r, then we are at this end here. If S' is 0, then we are at this end. And because we are dividing S' with the length of r, this is what similar triangles gives us, although in the similar triangles this division is actually between those two legs, but the length of r is also repeating up here. Then this division, what it gives us is the percentage we are along this axis up here. Or in other words, the percentage we are along this side of the cube map. Coincidentally, this RH divided by CM, this is also the tangent of alpha. Well, alpha is down here, the angle that we are sampling at, and well, the tangent of alpha is going to be from -1 to 1, when alpha is from -45 to 45. And this 45 degrees, this is the largest angle that we can sample from this particular face of the cube map. In code, it might look like this. So you have your cube map sampler cube, you have some normal vector and the position. you normalize your normal vector, you take the normalized position as the incident vector, because right here we are working in camera space, and we reflect the incident vector along normal vector, getting the vector R, and this texture cube called on my cube map and R samples the cube map with the logic we just saw in the video. Now it might look a bit weird, so we're rotating the camera and the reflection on this sphere always stays the same. Why is that? Well, the reason is that all of our vectors here are in camera space. So this reflection vector, it is represented in relation to the camera. So when the camera rotates, the coordinates of this reflection vector don't really change. To fix that issue, you should actually do this calculation in world space, or you move your reflection vector into world space using the model matrix of the camera. So this is the inverse of the view matrix, or the model matrix of the camera, that takes camera space coordinates and moves them into world space. If you move your reflection vector into world space and then use it to sample your cube map, then you can see that the reflections are changing as the camera is rotating around this reflective object. From this video, you should understand environment mapping, its purpose, so either to show some kind of a skybox of distant objects, or to save this illumination in the environment and then sample it for reflections. We learned about a cube map. We saw a couple of ways to create a cube map. So you can draw it, you can take it with a 360 camera, or you can render it in real time in your game. We saw that it's stored as these 6 equirectangular textures, and it's a common assumption that this cube map, the image that it represents, that it's infinitely far away, because we're sampling with that assumption, we're sampling with the reflection vectors centered at the center of the cube map. We saw how the reflect method is actually implemented and what does it do geometrically. And we looked at the math behind this cube texture sampling. And we saw a potential issue that if your reflection vector is in camera space, then all of your reflections rotate together with the camera. The reflection vector really doesn't change if you're rotating the camera. But it makes more sense to have the cube map in relation to the world. So you move your reflection vector into world space, sample the cube map from there, and then you will get the reflections that you would assume.